All right. So in chapter 9, what we started talking about was about termination life cycle or process when Carpenter removes a node, not only for efficiency, like for simple consolidation, but there are also other actions that could remove a node. We briefly talked about in the previous episode about voluntary and involuntary interruptions. Involuntary interruptions are those who are, for example, the node expiration, spot interruption, something is happening with the node because they have a health issue. Those are the interruptions that you can control. And when you, for example, when you receive a spot interruption, you have only 10 minutes, and we talk about that as well, how Carpenter handles that. There are other voluntary disruptions, for example, deconsolidation. We talked about that in the previous episode, that this is basically covering, or this is simulation that Carpenter does when to look for opportunities to either replace a node or to delete a node. Replace a node with a smaller one, with a cheaper one, or to basically evict some pods from under-reserved or underutilized nodes so that the kube scheduler will reschedule those pods. And in a way, it will leave a node empty, so it will be removed. That again is also for efficiency. And another reason for voluntary disruptions are drift operations. And this is where I would like to focus on the first few minutes. And again, as I was saying before, feel free to interrupt me, feel free to send any questions over the chat, although I might not be able to pay attention to the chat very closely. So if you can unmute yourself and ask a question or say something, go for it. All right, so the drift operation is basically as in the Kubernetes ecosystem, there are a few other kind of like this paradigm or this way of working is very common into from the controllers that you have in Kubernetes, and Carpenter is no the exception. So you have here our conciliation approach in Carpenter that it's gonna detect that the desired state of the configurations have drifted from what they were supposed to be doing, and that will apply essentially for node pools and node classes. So in this part, what I'm giving you as an example, for instance, is like for you have a new version of, for example, the AMI, in this case, Bottle Rocket. I think that 142 is already too old, but let's say, for example, that we release a new, or Bottle Rocket release a new version of their OS. So we therefore we release a new AMI, and that will be effectively drifted if you already if you change the version of the alias, right? I think that I'm gonna be covering this later, but usually where you see in the samples is that for the alias, instead of specifying the version here, people tend to, or the samples, or even AI tends to put latest. And you have to know the consequences of using latest here, because that means that it's gonna always use the latest version. So therefore, as I was saying before, right, when we release a new version of the OS, in this case, Bottle Rocket, it's gonna be drifted from its configuration. So it's gonna force a voluntary disruption into the nodes from your node pool, and those are gonna be replaced. So if you want to avoid that, and if you want to control that, it's recommended to have a specific version of this. For example, in this case, I'm using 142. I was using 142. A new release came out, and then I changed intentionally my node class to 143. As soon as I push that change into the cluster, Karpenter will notice that there is a drift in the configuration from the existing nodes that you have from that node pool, and it's gonna start to replace the nodes, right? So I cover here what causes the drift. Of course, this is at the time of writing. Nothing has changed significantly here, but anything like the new AMIs, or if you change the instance families, or hardware changes, like for example, if you migrate to If you in your node pool you add ARM or Graviton, or if you change, for example, the purchase option like Spot, if you add Spot, chances are that Karpenter again is gonna either consolidate it, or it's gonna be able to drift, or it's gonna replace the nodes because its configuration drifted, right? Same applies to, for example, in your node class, if you change your networking or security groups. And this is very interesting, the Kubernetes version, because there is a blog post. I don't have it handy, but I think I included here in the notes of the book. There's a common pattern when you need to upgrade your cluster. This is very easily achieved. You can achieve this very easily with Karpenter, because when you change the control plane, let's say, for example, now to the newest version 1.36, the nodes registered to the cluster right now will be effectively working with 1.35. Because you updated the control plane, the nodes into the cluster are drifting its version. Therefore, this is forcing a drift operation, and Carpenter will start to replace the nodes progressively so that they match with the control plane. This is a very common pattern. There's a blog post that we wrote I think a few years ago, um, where we talk about this pattern and where we address how to do it and how to take care of it. But it's a very common use case to use it as an upgrade mechanism for the cluster. Have a tons of customers doing this operation with Carpenter, and it's a no-brainer, right? And then I guess that um managing drift carefully, this is basically I'm covering uh tips and tricks that you would like to get into place. And I'm gonna be covering here in the next topic here how to take care of not just the drift operations or constellation operations, but constellation operations as well into a node, right? So before I jump into that, well, I have here a lab into the book in the book where you simulate the updating of the AMI. I noticed that I could have done, it would be really cool to have done the upgrade of the cluster, but it will take too much time. And I wanted to keep it simple here so that you can actually see in action the drift operation. But again, happy to share that link with you if you're interested later on how to do the upgrade of the node of the cluster, um, taking advantage of this operation, right? There's another uh, there's another thing into Carpenter in terms of termination. We already talked about consolidation, drift operation, and there's another aspect where you can configure like TTL of the nodes. By default, you can specify here, for example, a default of expire after 30 days. That will mean that every 30 days, the nodes will be expired and will be recycled and will be terminated, will be cordon and drain, wait for the node to be ready, and you will have a fresh node. I think I covered this. Why would you like to do this? It will be useful in terms of, for example, security. You can get the latest version of the CVEs that have been fixed, have been patched in the recent AMI. Or if you're using, for example, Spot, remember that with Spot instances, you get instances from the deepest pool of capacity at that point in time. 30 days later, that might not be the case anymore. Or maybe 5 days later, that might not be the case anymore. And you would like to recycle the nodes automatically for in terms of capacity as well. By the way, this is when the expiration comes in, there's nothing you can do about it because it will be and it will fit into the involuntary group of actions. So bear in mind that this is something that you will need to take care of it as well. There is another thing here that you can put into the node pool as well that is called termination grace period. Um, that you have, for example, for the pods. You also have something similar for the nodes as well. I think I have, yeah, it's the same label as you have with, for example, with pods. With node pools, you will have a termination grace period, meaning that it's basically a time frame that you are allowing to the node that when you do a cordon, a drain, and the node might not be terminated, you basically have a way of forcing the termination of these nodes. Another use case, in the beginning, when Karpenter was released, there were some edge cases where the nodes were stay there, hanged, stuck because of reasons, and the nodes won't be removed or replaced. So that's why the Karpenter team decided to introduce this mechanism in place or into the node pool so that the nodes can be terminated after a certain amount of time, right? So this is kind of like a safety mechanism as well, and you can play around with this. And then that's basically taking me to the other topic that I wanted to highlight or to bring from this chapter, which I think it's very useful, and it's the no pool disruption budgets. We already talk about again consolidation, drift, involuntary disruptions like node expiration, spot interruptions. No pool disruption budgets are similar to pod disruption budgets, but for the nodes. Although I'm saying it's similar, it's simply I'm just saying that it's just a way of um, for you to understand what this configuration looks like or the purpose of this configuration are, but it's the devil is in the details, as I would like to say, as I like to say, right? But no pull disruption budgets work effectively only for voluntary disruptions, right? So that way, that means that you can say, for example, the simplest configuration on the default one that you have, it's gonna be like this. In the node pool, you can have a disruption budget nodes 10%. That effectively means that 10% of the nodes can be disrupted at the same time, right? It doesn't mean that only 10% of the nodes will be disrupted and then the next 10% of the nodes. It doesn't work that way. Say, for example, that you have um, 100 nodes that you need to expire or that you need to replace because it's a drift operation, and then you need to work into controlling that. So that means that effectively 10% will be 10 nodes. 10 nodes will start to be replaced, but let's say, for example, that 2 or 3 nodes will take their time to be replaced. That will be fit into the budget. That will leave you with 7 nodes that can be entered into that window. So instead of taking 10 extra nodes, it will take 7 nodes. Not sure if that makes sense, but what I'm trying to say here is that only 10% of the nodes can be interrupted at the same time, regardless of how the operations will work and how it will look like, right? So you can see here effectively what I mean by this, how many will be interrupted, and it's just basically disrupt 2 nodes, in this case, concurrently, right? And that's the simplest operation, but what is really cool is that you can define schedule as well. Because one of the things or the pushbacks that I got when working with customers at the beginning with Karpenter was that, hey, Karpenter works really well when creating the nodes, when launching the capacity. It works really well when you need to replace the nodes because you need to run consolidation. Uh, but for some of our customers, Carpenter was doing a job that it was too aggressive. Actually, in fact, last week, last week, I had a session with a customer in Spain, kind of like Uber, but it's the local brand. It's called Cabify. And they share on stage with me that they basically, when they start to adopt Carpenter, one of the things that they notice is that the nodes were starting to be replaced because of the underutilization aspect of it. So consolidation was actually causing a downtime into their application because they didn't expect that Carpenter will be too aggressive on replacing the nodes. I think that if I recall well, they did it the migration to Karpenter way before we had no disruption budgets, no pool disruption budgets. So they didn't have a way of managing that. They had to make sure that their applications were fault tolerant, and try to remove manually consolidation when they think that they had some crucial moments. But that was before that. Luckily, now if you use Carpenter, you have no pool disruption budget and you can specify schedules. So let's say, for example, that from 9 to 5, you don't want Carpenter to replace nodes because you have a drift or a consolidation operation in place. Um, and then, yeah, I share here the configuration, and it's similar to a cron configuration. You can say like, hey, how many in this case, what I'm saying is that from 9 to 5, for Monday to Friday, basically starts at 9, and effectively the duration is gonna be 8 hours. No nodes can be disrupted from this node pool. Outside of that window, do whatever you need to do. Okay? And then what we also added with no pool disruption budgets is a reason. Because then we have another set of customers saying like, hey, okay, this looks cool, but again, it's too aggressive. But I also would like to be even less aggressive with drift operation. Let's say, for example, a drift operation, I would like to run it on Mondays during a small window where I have the team focused, and if anything happens, they can proactively work on fixing any problem. Or we would like to do it in the morning, very early, or at night, things like that. But consolation, we would like to do it every day after the heavy traffic that we'll have in our clusters. So that's why we also have reasons. Again, things can get complicated very quickly, but you can have budgets for different reasons. So you can be um, much more aggressive in consolidation and much more conservative when you're drifting for a drifting operation. Okay. Lastly, you can have a mix and match as well. You can have multiple disruption budgets here into your notebook configuration. You can have, like as I was saying before, you can have for drifted and empty nodes, 20% of the nodes, and then for the rest, you can do the operations 5 nodes at a time, right? And then yes, of course, I go here over labs here, and I guide you on how to do it so that you can see effectively how this works. And yeah, I think apply that to Drift. I update the version of the bottle rocket, and yeah, that's it. Oh yeah, this is pretty interesting because I always got the question around pod disruption budgets, when to use it, when not to use it, and the reason for this, why I'm highlighting this, is because I worked with a customer that was running a Kafka cluster, and they were having issues when upgrading the cluster. The reason for that is because they needed to make sure that it was very um, conservative into the way on how you upgrade the cluster. So they had a very low budget of how many nodes or how many pods actually can be interrupted. But this is basically Karpenter will respect the PDBs, right? It will respect the PDBs and it will respect the no pool disruption budget or NDBs, as I like to call it. So make sure that, I mean, you're not too restrictive into this because that might cause some problem of efficiency into the cluster, and some nodes might not be replaced because of that will be a violation of the budgets that you have configured, right? So make sure that you have that in place. In the next chapter, we're gonna talk about it, how you can troubleshoot that, because most likely chances are that the nodes might not be replaced because of something like this. Then I actually cover just one paragraph of one question that I got constantly into the pod disruption budget when using spot instances. Like I said before, spot instances are involuntary disruptions into the cluster. So no matter what, no matter how restrictive your PDB is, spot interruption is gonna come and it's gonna reclaim the node. Okay, no matter how much restrictive you have the PDB, so you have to be careful about this and set your expectations to you and the team as well when using spot instances as well. This is very useful, especially when you're doing an update, an upgrade. But when you're doing when you're getting an involuntary disruption, then things are gonna change, right? So make sure that your applications are involuntary disrupted friendly, so to speak, when going into this. Then yeah, of course, before closing this chapter or this section, I go over no pool best practices and no class best practices. Like for example, as I was saying before, don't tag your alias into the latest version of it. Um, And for your notebook, keep it as flexible as possible. Let Karpenter to through the bin packing algorithm to decide which instance types are the best one for your unscheduled pods. Then for workloads, consider defining PDBs. Notice that I'm suggesting to use PDBs. Just make sure that you're not too aggressive into this. And yeah, I think that's it for chapter 9. Any questions or comments so far before we move to the next one? No? All right. Let's go with chapter 10 then. Okay, this is basically gonna be kind of like the almost getting into the end of the book. We have 3 chapters more, and chapter 10, if you notice the pattern, what I've been doing is that I've been including specifically how to work with Kera, go deeper into working with Kera, then a dedicated chapter into kind of like the operations, troubleshooting, debugging, and anything that you will find useful for troubleshooting your workloads. I'm replicating the same pattern here for Karpenter. However, this is gonna be a bit different because what I'm talking about here, of course, let's say it's a Kubernetes ecosystem. There's nothing new around here that you might not know already, in the sense of when troubleshooting your workloads or your controllers or what is running into the cluster. I'm not saying any different here that, for example, check your logs, check any metrics, and I'm explaining here that you will need to check your events as well. Actually, this was really cool because onto if you don't find something or if you would like to find what's going on into the logs, you will have a lot of noise there, so you might not be able to identify what's going on. Of course, now with your AI agents, it might be easier. I've been using my AI agent to troubleshoot a few times what's going on. So it's been really good. It's been really cool. However, if you want to go and actually instruct your agent to not just look at the logs, but also look at the events, you will find very useful information. So, for example, let's say that a very common thing will be to understand why a node pool or a node has not been disrupted. And you will be finding things like this in the events like disruption is blocked. Because, for example, you have a restrictive no pool budget that is not allowing the node to be disrupted, right? So going into the events, it's perhaps the easiest part of finding out what's going on into each object. Then, because of that, what I what I did at that point in time is that I scanned through the code, of course, using uh, uh, a search and replace operation. And I was able to create this table that you can see here of the type of events that you might find into, for example, Karpenter and the object type or where you will find that, right? Remember that we have at least three CRDs, the node claim, and the node pool. You can find those events into any of these types of objects, and you will find something, a message like this. And I'm including an explanation, a short explanation, what this means and why you're getting this type of message. I didn't invent this. I didn't come with this from out of nowhere. This is basically, you can get it from the code. That's what I was referring to on the search operation, because this is basically included into the code. I got this feedback from Jonathan Innes. If you remember him, he's one of the forwarders, and he was a key reviewer into the book, and he told me, hey, it would be nice to include a table reference with all the events, so you can go and use this and come back and look at the events that you get, and yeah, find out what that means if you don't want to go to the code and try to find out what's going on, right? Um, yeah, it doesn't, it's not worth it to go into each every table. I just wanted to each every item. Just wanted to highlight why is this important, right? Um, yes, this is yeah. I remember what I wanted to highlight this, because what I did at that point in time is that I documented here. There's, if you remember, if you know very well, there's a repository on GitHub where I include all the assets and all the resources for the labs of the book. And one of those assets is this file, eventsmd. It's gonna include all this table. So in case, I did it as a safety mechanism, because once you write the book, it's gonna be there forever. It's gonna be very hard to change its content. So if anything, I would like to update the list of events, remove or add or change it. The latest source of truth is gonna be the one you will have in this file into the repository. Okay. Then, of course, as I was saying before, there's nothing new about troubleshooting things on Kubernetes. The first one is gonna be events, and the other option is gonna be looking at the logs as well. In this case, I'm including an alias that I've been using it for workshops. So we've been running workshops for a while in AWS about Karpenter, and because we're used to reading the logs a lot, what we end up doing is to create an alias like KL. With this, it's just basically querying the latest 20 lines of the Karpenter pods, and it will give you the list of events logged, right? So in this case, you just run KL, and that's it. You can get that. I'm highlighting here as well another cool project from TAM within AWS, from AWS, that is called Log Parser for Karpenter. You can find this project on GitHub, and this is really cool because you deploy it, you install it in your computer, and you're gonna see here that it's gonna do kind of something like this, but with asteroids, as I like to call it, right? You can it's gonna create a CSV so that you can create a dashboard, or you can create a report with QuickSight or Power BI, or again your AI agent, and you can get this CSV file. So it's really cool, and I will highly recommend you to give it a look as well. Then of course recommend you how to keep this on your terminal every time that you open it. I found it very useful to do this. See, what I did here is I included all my tips and tricks for doing this, for troubleshooting clusters. Then of course, as a general recommendation,
Christian,
yeah,
could I interject? Could I interject? This is Jack Kozik.
yeah, tell me.
So, so at the beginning of this chapter, you mentioned something about your AI agent. So I typed in, the AI agent that I have managing my cluster. I
Yeah.
asked it, hey, what do you think about Carpenter, and how could you apply it to my setup?
Hmm.
And Claude Code knew all about Carpenter and gave me very reasonable suggestions on what to do with it.
Oh, nice,
Did
nice.
do you know that did Claude Code train on your book?
I don't
I
know.
doubt it, but it was
I
as
don't
if
know. I don't know.
have you ever prompted Claude Code on Carpenter?
Yes, so what I do is basically every time that I need to go deeper into troubleshooting something that I didn't knew because a new release came in or a GitHub issue is coming in, what I tell this in my case I'm using Kiro, what I say to Kiro is like, hey, go find out what's going on based on the logs that you see in my cluster, and compare that with the official docs, only the official docs, or if you can find out more information in the source code, because you will be surprised how many of this information is going to be there. Kind of like applying reverse engineering into this.
Yeah.
So I found it very helpful on this case. Um, so yeah, but you have to prompt it very precise on the sources that you want to use, because even though Claude or any other model might have already the information from Carpenter, I don't know if it's the book or the
Yeah. No,
official
I don't know
docs,
what it would be. But the thing
but
is, it didn't say Carpenter what? It knew exactly what I was talking about when I asked about it.
yeah,
So
but you will be surprised because a few weeks ago, I run a query into, hey, what mean values means in Carpenter. It knew about Carpenter, but it didn't knew about the mean values operation.
okay,
I'm not saying that models are not gonna be smarter. It's just a way of the data when they were trained, the data that they got, and you have to prompt it to go and get the latest information. If you don't do that, it might hallucinate, it might tell you wrong things
okay,
that might look authoritative. So you need to be
okay,
careful on that as well.
okay. Well, thank you.
Yeah. Um, yeah, this is really cool as well. So another feedback that I got from Jonathan Innes, if you recall him as well, he's one of the maintainers of Karpenter. He told me, hey, we've been including very useful information into the status conditions of the object. So might be a good idea to include this because it's really useful to go and explore that as well. And of course, you can, I didn't go into details here of why or what type of information you can get from here. But if you go and describe the event in the status conditions of every object of Kubernetes, this is true, and this is even true as well for Karpenter. No claim, no pools, and even the node and the pod and so on will report something into the status condition, and the Karpenter team has been included meaningful information to that. All right, so next time that you go into your agent and tell it to explore not just events, but also the logs and also the status conditions so that it can get a more comprehensive information and more solid data to actually tell you what's going on, okay? And yeah, then what I don't want to spend too much time on here because things are gonna get very messy if we go into each topic. But in this section of the chapter, what I wanted to cover is the common operational challenges. Because it's like a fairy tale, right? Every time that you see a demo or that you start using Karpenter and Keda, everything works flawlessly. Everything is looking really nice. However, when you start using it, you will be surprised how many people, how many customers are being uh, hearing that have been complaining, hey, as soon as we started using Carpenter, instead of cost going down, it went up. So chances are the nodes were not consolidated. There are a few reasons why I'm addressing here. Typically, the main reason is because your workloads are very restrictive. And for example, with affinities or topology spread constraints, and Carpenter, instead of being too aggressive, takes a conservative approach right now and say like, hey, you know best what you're doing. And if you have a restrictive constraint in your pods, like the ones that I mentioned before, I'll let you do it. And I'm not gonna consolidate because I'm gonna prioritize reliability before efficiency in these specific cases, right? So in this case, you might see that costs might go up simply because it's not consolidating, or maybe it's because your pods are requesting even more more resources than what they need, and Carpenter will just follow that. Okay, so I addressed that, and yeah, a few edge cases that I've been hearing as well. For example, when the nodes are not provisioned, not being provisioned, um, there are, for example, there's the problem of IP address exhaustion in subnets. This is very common, so to speak, in big clusters on Amazon EKS, where you get out of IPs and pods are not gonna be launched into the cluster, right? So, for example, the subnet doesn't have enough IP addresses. The instances launches and gets primary IP, but when the VPC CNA tries to assign secondary IPs to pods, none are available. So then the node will fail. And yeah, so I included to address this IP exhaustion problem, you need to consider the following recommendations. For example, spreading pros across more subnets. You can include more subnets into to kind of like extend the cider of their VPC and add more subnets. This is basically what I'm saying. He kind of like ordering in the priority of things that you will need to include or to address. If none of these works, which might be very unlikely, but I'm no one to talk about your environment. You know it better than me. Usually what we see with customers is like they might be using a custom networking, so that kind of like a dedicated private network into the cluster, and that's problem solved, right? Or maybe you should consider moving to IPv6 finally. It's been years literally that I've been hearing in the industry people moving away from IPv4, and I don't think that has happened fully yet. And then there, for example, capacity issues, being very specific about AWS here simply because I would like to highlight a few things, but this could apply to any cloud provider or any implementation of Carpenter. But basically, there might be chances where nodes cannot be launched because there's no capacity. Typically, that happens because you are restricting your node pools to use only a few instance types, and you're not letting Karpenter to diversify as much as possible, right? So best practice, let Karpenter do its job. You just specify the families or the categories in this case, and let it be. Let it Karpenter to choose that. Unless you have a workload that has a restrictive set of instance types that they can use because they benefit from performance optimization or because they're very low latency sensitive, then of course you can balance that. The way that I like to address this, I highlighted this in a CNCF blog post and in my sessions as well. Think of it like a triangle. You have a triangle with each corner where you have reliability, you have another corner of performance and cost. All of these corners stretch themselves, so you can optimize for cost, and you might sacrifice, for example, performance because you are optimizing for spot, and you might not get the latest generation of instances, but what is left in terms of capacity. So then the performance might degrade a little bit. But if you go into improve the performance, then of course you're gonna prioritize the latest generation. Cost might go up slightly depending if you are taking advantage of the performance and again reliability, right? So we can talk about that. I actually covered that at the end of the book as well. Yeah, quota limits, constellation failures here. Basically, what I added here is anything that I've been getting constantly from customers, from what I'm been hearing from colleagues as well. And I actually went as well into explore a few GitHub issues and what were the common edge cases or problems that people were having. So it's not perfect. It's not covering any all of the edge cases, but I'm covering the most common ones. And if you read carefully here and slowly, you're gonna see that I'm reflecting back into the basics of how Carpenter works, and kind of like the best practices that I recommended in the previous chapter as well. Another cool feature that Carpenter released as well, again, because the project has been evolving and maturing a lot over the years and months as well. There were some edge cases where the nodes were hanging out. So we released termination very experience as well, but we also released the feature of node auto repair. So in this case, for unhealthy nodes. So imagine here that you have a node that is not being terminated because of reasons, because in this, for example, if we're talking about GPUs, the GPU devices failed, and there's no way that the node can be terminated. So there are ways that you can terminate or force the termination of those nodes by using this feature, node auto repair. Okay, I call it NAR. Simply because I wanted to simplify and use it as a acronym here. So this diagram you can see here is just basically working in tandem with, for example, in this case, with no monitoring agent. And I think I have here a note. Uh, I'm saying no monitoring agent because there might be there are, for example, we have on AWS an agent specific to our ecosystem, but there are open source agents as well. Don't remember exactly the name of it, but I included here in the notes. I'm gonna say it when I see it here. So yeah, it's gonna work in tandem with that, and typically those mm, Carpenter it's gonna get the events from no monitoring agent as well. So like for example, if the node is not ready for 30 minutes, like in this case, once toleration duration expire, in this case 30 minutes, it will force the termination of the node. Here you can see here that, for example, not ready, it's gonna be 30 minutes if it falls, and if it's unknown, it's gonna be 30 minutes. If you have, for example, accelerated hardware ready, this is a type of event that in combination with a node monitoring agent and Karpenter feature, that will react a little bit shorter, or it's going to be more aggressive. So after 10 minutes of having this error, it will replace the node. Storage ready, networking ready, store faults, kernel ready, or container runtime ready for 30 minutes. It will mark this as false, and it's gonna force the termination of that node. Then, yeah, I think I have here how to enable it, because right now it's in alpha, and you have to enable it intentionally. You have to opt into this feature. And yeah, of course, I have a lab here. It's interesting for this lab because of course you have to enable it. And then while I was building this lab, I actually had problems. Even if you don't think about it, if you never thought about it, I had problems trying to make sure that the node was in a failure mode. The reason being in this case, because I was using EKS, I was, for example, I don't remember exactly how many things I tried, but everything that I was finding out in the internet about how to make the node, put it in the failure node, like not ready, like bringing the network down, removing the internet, or things like that. EKS was fixing that automatically. So what I did is I ended up creating an application here. Yeah, inject a failure into the node, and that basically that script has I think it's a script and not a container. I don't remember exactly right now. We can look at the code, but it's and I didn't specify it here in the book because as I was saying before, right? Once you write a book, it's hard to update the book, and it's easier to update the script. So if anyone here at some point reports to me that the lab stopped working because they cannot reproduce the failure of the node, I can easily go and change this. So at the time, right now, it's basically forcing the failure of containerd in a very messy and insecure way, to say the least. Okay, so be careful of that. It's just, again, it's just for demo purposes, lab purposes, but I wanted to show you the failure of a node. When we released this feature, the node auto repair feature in our blog post, the example or the demo that we did is we caused a failure to the GPU drivers. That's easier to reproduce, but I didn't want you to force you to launch a GPU simply just to test this feature, right? So I managed to get this script to force the failure, and yeah, it basically worked. After 30 minutes, you have to wait for 30 minutes, and then it will replace the node automatically. So if you don't believe me, go give it a try and let me know your thoughts. Then similar to what we have with Kera, we have it for Karpenter as well, upgrading Karpenter. And because I didn't want to basically repeat what we have in the Karpenter docs, because I think that the Karpenter team has done even a way better job of giving you instructions on how to upgrade the cluster. Of course, again, same pattern that I shared before, right? It's easier to update GitHub links or docs with how the process of upgrading Karpenter will be. And in every major change, the Karpenter team might decide to change the instructions slightly because of a disruption that could happen, right? So, but what I'm including here in the book is kind of like a general practices, right? It's 4 stages. It's kind of like pre-upgrade checks. uh, Pay close attention to the CRDs, that the new version of the CRDs. Typically, this comes into the release notes. By the way, we released a new version yesterday about Karpenter. And if you look at the release notes, they include the changes that you need to be aware of. Like, for example, breaking changes of CRDs, similar to, again, it's nothing different to what you will have in Kubernetes upgrade, so to speak. We report changes that have been that are gonna happen into the CRDs. We have a process of um, removing certain labels and not being supported in the next version and things like that, right? Then second stage will be stage the upgrade. Kind of like in this case, what I'm saying is that test in smaller, in lower environments before going to production. It's common sense and test it, right? So do it this, consider during a maintenance window if you have one. If especially if you're getting started into this, so that you are not caught into a failure here. And as you get more confidence into this, you will be able to do it easier. If you are finding problems or typical issues that you might have here, you can go to troubleshooting here in the docs. Typically, Karpenter team will report a few things over here as well. The post upgrade verification. Notice that I'm using the alias that I mentioned before, right? Cancel here. And yeah, here then observability and metrics. What's really cool about Carpenter here as well and these projects, you're gonna notice that we're following the same or similar approach to what Kera did. So Carpenter team is deploying already a Grafana dashboard based on the metrics that the Carpenter controllers are exposing in a Prometheus format, right? So the Carpenter controllers are gonna have certain metrics that you can look at it. And all of those metrics are actually documented in the docs. And similar to what I did in the table for the events, the Carpenter team is using that for the metrics. I didn't want to waste paper because the Carpenter team already documents the type of metrics, all the metrics that are being reported into the docs. I didn't want to do that. However, what I did here is kind of like I kind of like uh, group certain metrics into, for example, cluster resource utilization. So to get the percentage of the cluster allocatable reserved CPU memory currently requested pods, you can refer to the metric called Carpenter cluster utilization percent. And I give you a few recommendations about it. And then for scaling activity, see what I did is basically based on what I've seen with other customers as well, I just kind of like grouped the metrics and little by little I was explaining to you how to make sense out of them, right? Because the metrics that you find there may not be well explained, or the explanation might not be enough for you if you don't have experience over it. Then, of course, I divided into different categories, but startup time, things that you might be interested in, look at it. For example, this metric is especially designed to monitor from a Carpenter scheduler, not to count all pending pods in a cluster, for instance, right? Then I go over here as well, other metrics. And then, as I told you before, Carpenter comes with a Grafana dashboard, and that's exposed as a Helm chart as well. No, not a Helm chart. Sorry. Here is basically I'm reading this and thinking about it at the same time, but I'm including here Prometheus, Grafana, and before setting up onto the lab, then I deploy the service monitor, and then I make sure that it's working, and then here it is. I deploy the Grafana dashboard, which is being included as a JSON format into every version of the every release under this location, right? So I'm using the preview to get kind of like the latest version of it, and that will show you a diagram like this, or a dashboard like this, sorry. So you can see here the disruption controller, the queue, the reconciliation loops. This is basically the dashboard that I got from all the tests that I did. And that's it. That's it. That's what we have for chapter 9 and 10.